During the Second World War, minefields and fortified obstacles posed a serious challenge to advancing armies, often slowing or halting armored operations entirely. To overcome this problem, Britain developed a wide range of specialized mine-clearing and demolition vehicles, many of them unique in both design and purpose. This video examines every British mine-clearing and demolition vehicle of the war, from flail tanks and rollers to explosive systems and experimental designs. We will begin with the British flail tanks. Flail tanks were developed to clear safe paths through minefields by detonating mines ahead of advancing forces. Britain pioneered this approach as a practical response to heavily mined battlefields. Sherman Crab. The Sherman Crab was developed to provide a reliable, purpose-built solution for clearing dense minefields during assault operations. Contrary to popular belief, it was not intended for direct combat but for enabling movement through prepared defenses. Built on the M4 Sherman chassis, its rotating drum and chain system reflected a balance between mechanical reliability and effective mine detonation. The Crab saw extensive use during the Normandy landings and across northwest Europe, where it enabled infantry and armor to advance with reduced risk. This success encouraged further refinement of earlier British flail concepts. Matilda Scorpion. The Matilda Scorpion represented Britain's first operational attempt to fit a flail system to an armored vehicle. Developed in response to Axis minefields in North Africa, its externally driven flail mechanism demonstrated that controlled mine detonation was feasible under combat conditions. Although mechanically crude, the Scorpion proved that flail tanks could operate alongside frontline units and shaped all later British designs. Experience with the Scorpion led directly to more ambitious flail systems, Matilda Baron Reaper II and III. The Matilda Baron series was developed to improve upon the limitations of the Scorpion by increasing flail power and durability. These variants used external engines to drive heavier flail mechanisms, reflecting an engineering effort to increase clearance effectiveness rather than combat capability. While the Baron tanks were never widely deployed due to mechanical complexity, they provided critical data that influenced the design of later, more reliable flail tanks. These experiments highlighted the need for a more adaptable chassis. Valentine Flail. The Valentine Flail trials explored whether a lighter, more mechanically efficient tank could support flail equipment. Designed to evaluate alternative layouts and drivetrains, these experiments demonstrated that not all chassis were equally suited to flail operations. Although the Valentine Flail did not enter service, it contributed to a better understanding of weight distribution and suspension requirements. Britain also examined heavier platforms for flail operations. Churchill Flail. Churchill Flail experiments were conducted to assess whether a heavily armored tank could carry more powerful flail systems. These trials reflected the belief that increased protection could allow mine-clearing vehicles to operate closer to enemy fire. While never standardized, the Churchill Flail concepts informed later engineering vehicles by clarifying the trade-offs between armor, weight, and mechanical complexity. With flail tanks established as Britain's primary mine-clearing solution, attention turned to alternative methods based on mine rollers and ground pressure systems. Mine rollers and trackway systems. Mine rollers and trackway systems offered an alternative approach to mine clearance by triggering explosives through weight or providing safe surfaces for vehicles to cross. Britain explored these methods to complement flail tanks in varied terrain. Canadian Indestructible Roller Device. The Canadian Indestructible Roller Device was developed to clear mines by absorbing detonations through heavy steel rollers mounted ahead of a tank. Designed to operate under repeated blasts, the CIRD reflected a simpler mechanical solution compared to flail systems. Although its weight reduced speed and maneuverability, it enabled armored units to advance through mined areas without relying on rotating mechanisms. This approach encouraged further experimentation with roller systems. Sherman Tumbler Mine Roller. British trials of the Sherman Tumbler mine roller examined whether roller systems could be effectively paired with a standard medium tank chassis. The design aimed to provide controlled mine detonation while preserving the Sherman's mobility. While results were mixed, these trials contributed to British understanding of how roller systems affected steering, suspension, and operational endurance. In parallel, Britain explored roller solutions for heavier tanks. Churchill Mine Roller. Experimental mine rollers fitted to the Churchill tank tested whether a heavily armored platform could support sustained mine-clearing operations. These trials demonstrated that while increased protection improved survivability, added weight placed significant strain on mechanical components. The results reinforced the need to balance protection with reliability in mine-clearing vehicles. Beyond rollers, Britain also developed systems to bypass mines rather than detonate them. Churchill Bobbins. The Churchill Bobbins system laid a continuous trackway in front of advancing vehicles, allowing them to cross soft ground and suspected minefields safely. Rather than clearing mines directly, bobbins provided a controlled surface that reduced the risk of detonation. This system proved especially useful during amphibious landings, where ground conditions were unpredictable and time was critical. These solutions demonstrated that mine clearance could be achieved through multiple engineering approaches, leading to the development of dedicated demolition and assault vehicles. Demolition and assault engineering vehicles were developed to remove obstacles that mine clearing alone could not address. Churchill Havre. The Churchill Havre was developed to solve the problem of fortified obstacles blocking armored advances. Contrary to common assumptions, it was not intended as a conventional combat tank, but as a mobile engineering platform. Armed with a short-range petard mortar, the AVRE was designed to destroy bunkers, concrete emplacements, and roadblocks. Its use during the Normandy landings demonstrated how specialized vehicles could open routes for infantry and armor rather than engage enemy forces directly. This capability was expanded through vehicles designed to overcome physical gaps in the battlefield. Churchill Arc. The Churchill Arc was created to allow armored units to cross trenches, walls, and other obstacles without the need for separate bridge-laying equipment. By converting the tank into a mobile ramp carrier, British engineers provided a practical solution for maintaining momentum during assaults. The ARK enabled following vehicles to move forward immediately once obstacles were breached, reducing delays under fire. To address terrain obstacles rather than fortifications, additional adaptations were developed. Churchill Fascine Carrier. The Churchill Fascine Carrier was designed to fill anti-tank ditches and trenches using large bundles of material carried on the vehicle's front. This approach reflected a simple but effective method of terrain modification under combat conditions. By allowing armored units to cross obstacles that would otherwise halt movement, fascine carriers played a supporting but essential role in coordinated assaults. Some British engineering concepts attempted to combine multiple roles into a single platform. Churchill Great Eastern Assault Vehicle. The Churchill Great Eastern was a prototype designed to integrate ramps, rollers, and other assault equipment into one vehicle. Developed to address the complex demands of fortified landings, it reflected an ambitious attempt to centralize engineering functions. Although it never entered service due to size and complexity, the Great Eastern highlighted the extent to which British planners prioritized engineering solutions over traditional combat roles. Alongside these armored vehicles, Britain also developed explosive systems intended to clear minefields rapidly. Explosive delivery systems were developed to clear minefields rapidly by creating instant lanes through detonations rather than relying on repeated mechanical contact. These systems reflected Britain's effort to reduce exposure time during assaults. British Snake Explosive Charge. The British Snake was developed to clear paths through dense minefields and wire obstacles using a long, flexible explosive charge. Rather than detonating individual mines, the Snake created a continuous blast corridor across defended ground. This method was particularly useful when speed was essential, allowing infantry and vehicles to advance through previously impassable areas. This concept was later refined into a more advanced system. Conger Mine Clearing Line Charge. The Conger system was designed to improve upon earlier line charge concepts by using a rocket-propelled hose filled with liquid explosive. Contrary to some assumptions, Conger was not intended as a precision tool, but as a rapid clearance method for large minefields. Although effective in trials, the system was withdrawn after accidents revealed the risks associated with handling liquid explosives under combat conditions. Its development nonetheless influenced post-war mine-clearing technology. As British engineers continued to search for safer methods, attention turned toward removing crews from direct exposure during clearance operations. Remote-controlled and experimental systems. Remote-controlled and experimental systems were developed to reduce the risk faced by crews during mine clearing and demolition operations. These designs reflected an effort to apply emerging technology to particularly hazardous battlefield tasks. British remote-controlled flail prototypes. British engineers explored remote-controlled flail systems as a means of clearing minefields without exposing crews to direct danger. These prototypes adapted existing flail mechanisms to vehicles controlled from a distance, allowing mines to be detonated ahead of friendly forces. Although limitations in control technology prevented widespread adoption, the trials demonstrated early interest in unmanned engineering solutions. This work extended to other forms of remote demolition. British remote demolition carrier experiments. Limited experiments were conducted using small, remotely operated vehicles to deliver demolition charges against obstacles and fortified positions. These designs were influenced by the same operational concerns that drove flail development, prioritizing crew survival over mechanical simplicity. While none entered operational service, they reflected a broader recognition that some engineering tasks were too dangerous for manned vehicles. These experimental efforts marked the final stage of Britain's wartime approach to mine clearing and demolition. British mine clearing and demolition vehicles reflected a consistent focus on solving specific battlefield problems rather than achieving combat superiority. From flail tanks and mine rollers to assault engineering vehicles and explosive line charges, each design was shaped by the need to maintain momentum in the face of heavily prepared defenses. These machines enabled infantry and armored units to move forward where conventional vehicles could not. Although many of these systems were produced in limited numbers or remained experimental, their development demonstrated how engineering innovation became central to British operational planning during the war. Together, they illustrate a practical approach to warfare in which mobility and obstacle clearance were treated as essential elements of battlefield success rather than secondary concerns.